In 1982, a computer too expensive for the average family quietly took over 80% of UK schools. The BBC Micro was a premium, heavy-duty machine. With its striking red keys and steep price tag, it should have been locked away in corporate offices. But it wasn't, because the British government stepped in and paid half the cost. This elite hardware became the absolute standard in British classrooms. The consequence was profound. An entire generation of students learned to code, play, and think on a platform the rest of the world would soon ignore. The paradox is that the BBC Micro did not succeed because it was affordable. It succeeded because Britain decided the digital future was worth subsidizing. But the real story of the BBC Micro is not just about a heavy beige box on a metal TV cart. It is the story of a public service dream that built a massive domestic ecosystem. And what happens when a generation raised on a British standard is forced to graduate into an American-dominated, IBM-compatible world? Every week, we tell the stories of the British home computers, high street shops, and classroom machines that once taught the country what the digital future felt like, and what happened when the global market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a sudden national panic. Inside the corridors of the BBC in 1981, the story begins in a state of national anxiety. By 1981, the microchip was quietly transforming global industry, yet the British public remained largely disconnected from the digital revolution. A documentary aired by the BBC, titled The Mighty Micro, warned that Britain was in severe danger of falling behind. In response, the broadcaster did something entirely unique to the British public service mandate. It decided to teach the entire nation how to program. This was the genesis of the BBC Computer Literacy Project. The BBC planned an ambitious television series that would explain computing not as an abstract science, but as a practical, everyday tool. But television broadcasts alone were not enough. The BBC realized they needed a physical machine to accompany the lessons. They needed a standard microcomputer, a small, relatively affordable computer designed for a single user, built around a central microprocessor, that viewers, hobbyists, and schools could actually buy to follow along with the code on screen. Before this moment, the British computing landscape was a fractured, experimental frontier. Enthusiasts bought primitive hobbyist kits or imported expensive American machines. There was no default system, no shared language. The BBC set out to crown one, issuing a list of punishingly strict technical specifications for their official machine. They demanded high-resolution graphics, a structured programming language, and analog ports, physical connections that would allow the computer to interface directly with real-world equipment like temperature sensors, motors, and robotic arms. The contract promised more than just guaranteed sales. It promised national legitimacy. The battle to win it took place entirely within the intense, claustrophobic ecosystem of Cambridge, a city that was rapidly becoming the Silicon heart of Britain. Two local companies emerged as the primary contenders, locked in a bitter personal and professional rivalry. On one side was Sinclair Research, led by the brilliant and relentless Clive Sinclair. Sinclair was already a household name, famous for driving down the cost of consumer electronics and bringing technology to the masses. On the other side was Acorn Computers, run by Hermann Hauser and Chris Curry. The tension between the two camps was palpable because Curry had previously worked closely with Sinclair before leaving to establish Acorn. The two companies occupied offices just a short walk from each other, constantly vying for the same engineering talent in the same high-street dominance. Sinclair pitched an early version of the machine that would eventually become the legendary ZX Spectrum, but the BBC felt it did not fully meet their stringent, heavy-duty requirements for education. Another early candidate, the Newbury Newbrain, also failed to deliver on time. Acorn saw a narrow window. They presented a bold proposal for a machine they called the Acorn Proton. It was a dual-processor design, boasting massive expandability and a fast, elegant version of BASIC, a beginner-friendly programming language that used English-like commands to instruct the machine. The BBC was intrigued by the specifications. They informed Acorn that they would visit their Cambridge offices on a Friday in April 1981 to see the working prototype in action. There was only one problem. The Acorn Proton did not exist. It was nothing more than a paper design. When Herman Hauser accepted the Friday meeting, he knew Acorn had exactly 4 days to turn a stack of theoretical schematics into a functioning, breathing computer. What followed is one of the most frantic and famous weeks in British engineering history. The impossible task fell primarily to Acorn's chief engineers, Sophie Wilson and Steve Ferber. Building a prototype in 1981 was a deeply physical, exhausting process. It required soldering thousands of connections by hand, routing delicate wires across naked circuit boards, and hoping the fragile logic held together under electrical load. By Thursday night, the night before the BBC delegation was due to arrive, the machine was fully assembled, but it refused to boot. The engineers frantically traced the fault to a timing issue with the processor, the main chip that performs the mathematical calculations and executes instructions. In a desperate final push, they physically severed a wire and soldered a resistor directly onto the board to artificially alter the clock signal. On Friday morning, the BBC team arrived at Acorn's offices at Market Hill in Cambridge. They walked into a room thick with exhaustion and the sharp smell of soldering flux. The Acorn Proton, a mess of exposed wires and raw circuitry, was powered on. It booted. It ran its operating system, the core software that manages the hardware and lets other programs function. It successfully displayed graphics on a standard television screen. The BBC delegates were astounded by the speed and stability of the machine. The Proton was fast, robust, and incredibly versatile. In that small Cambridge room, the decision was made. Acorn had won the broadcast contract. The rushed paper design known as the Proton would be officially rebranded, manufactured, and sold to the nation as the BBC microcomputer. This victory instantly transformed Acorn from a successful local tech startup into a national institution. They had secured the ultimate public service endorsement, but the reality of the contract was terrifying. The BBC had demanded a highly complex premium machine, and now Acorn had to mass produce it. They had to source thousands of chips, design a heavy-duty plastic case, write comprehensive manuals, and build a supply chain capable of delivering a flawless product to eager schools and households across the UK. The prototype had survived the weekend. The company now had to survive the manufacturing reality. A machine built by hand in a Cambridge office was about to be dropped into the chaotic, unforgiving environment of the British education system. Acorn had won the broadcast. Now they had to build the machine that would survive the classroom. The machine that arrived on the British market in late 1981 was not a fragile consumer toy. The BBC microcomputer system, manufactured by Acorn, was housed in a massive wedge-shaped beige casing of thick, reinforced plastic. It was physically imposing, designed specifically to survive the hostile environment of a secondary school classroom. While competitors were selling cheap rubber-keyed devices that slid around a desk, the BBC Micro featured a heavy-duty, full-travel mechanical keyboard. At the top sat a row of striking red function keys, a visual signature that would become instantly recognizable to millions of British pupils. Acorn released 2 main versions, the Model A and the more popular, more powerful Model B. To understand the breakthrough of the Model B, one must look at the back of the machine. It was lined with an unprecedented array of physical connections. There was a standard television output, a printer port, a serial port, and an analog-to-digital interface. This was not merely a home computer, a machine designed to sit in a living room and play games. It was an electronic nervous system. In a school science lab, a teacher could plug a temperature sensor directly into the back of the BBC Micro to monitor an experiment. In an engineering class, pupils could write code to drive a motorized robotic turtle across the floor. The machine turned abstract mathematics into physical movement, but this heavy-duty engineering created a massive commercial problem. The BBC Micro was punishingly expensive. When the Model B launched, it cost $399. In 1982, that was a staggering sum for a British family, roughly equivalent to a month's wages for an average worker. Sinclair's ZX81, by contrast, could be bought for under $70. Acorn had built the perfect machine for the BBC's computer literacy project, but they had built a machine that almost no ordinary household could casually afford. If the BBC Micro had been left entirely to the open retail market, it might have become a niche, high-end curiosity for wealthy hobbyists and university laboratories. Instead, the British government quietly altered the course of digital history. The Department of Trade and Industry, or DTI, was growing increasingly concerned about Britain's economic future. They believed that if the country did not rapidly adapt to the microchip, it would lose its industrial edge entirely. In April 1982, the DTI launched the Micros in Schools scheme. The premise was simple but unprecedented. If a secondary school wanted to buy a microcomputer from an approved list, the government would pay half the cost. The scheme was soon extended to primary schools. This single policy changed the British technology landscape overnight. Local education authorities across the country suddenly had the budget to buy serious hardware. When head teachers and council buyers looked at the approved list, they saw a few options, including machines from Research Machines and Sinclair. But the BBC Micro possessed the ultimate advantage. It carried the trusted BBC name, it was heavily featured on national television every week, and its rugged construction meant it would not break when a classroom of 12-year-olds hammered the keys. With the DTI paying half the invoice, the $399 price tag was no longer a barrier. It was an invitation. Schools bought them by the thousands. The BBC Micro quickly secured an astonishing 80% of the UK educational market. It became the absolute standard. Entire school computer rooms, dedicated spaces that had never existed before, were built around the beige Acorn machines. Because schools were buying them, a massive supporting industry sprang up. Companies began manufacturing heavy metal trolleys designed specifically to hold a BBC Micro, a cassette tape, magnetic tape used by many home computers to load and save programs before discs became standard, and a bulky square-color television, a school computer, a machine bought specifically for classrooms, lessons, and computer clubs, had transformed from a theoretical concept into a physical piece of furniture that was wheeled from room to room. The technical foundation of this success was its software language, BBC Basic. BASIC was a programming language that used English-like commands to instruct the machine, but Acorn's version was exceptionally fast and beautifully structured. Despite the Model B possessing only 32 kilobytes of memory, fast temporary storage a computer uses while programs are running, its core architecture used that space with brutal efficiency. It allowed pupils to type a few simple lines of code and immediately see a shape drawn on the screen. It offered instant, satisfying feedback. It also included a built-in assembler, meaning advanced users could write directly in machine code, speaking to the processor without translation. The machine did not patronize its users. It offered a shallow learning curve for a primary school pupil, yet possessed enough depth to challenge a university engineering student. This ubiquity soon spilled out of the classroom. Because the machine was so stable and its graphics were so reliable, the BBC itself began using the microcomputers for television production. BBC Micros were quietly installed in broadcasting suites to generate on-screen text, voting graphics for election nights, and even special effects for shows like Doctor Who. The machine was being used to broadcast the very culture it was teaching. By 1983, Acorn was not just a successful company. They were the architects of a national platform. They had secured the BBC brand, they had won the DTI subsidy, and they had physically placed their hardware on the desks of millions of children. They had built an ecosystem, a network of hardware, software, users, and publishers that made the platform increasingly valuable. The hardware was ready, the schools were funded, and the metal trolleys were rolled into place. But a computer only becomes a platform when people decide what to run on it. By 1984, the BBC Micro had ceased to be merely a product. It had become a fixture of British public life. To walk into almost any primary or secondary school in the United Kingdom was to encounter the beige, heavy-duty plastic of the Model B. It did not sit quietly on a desk. The BBC Micro was a physical event. Because the machine was heavy, and because the required square-color television and cassette recorder added to the bulk, a supporting industry of metal trolleys had emerged. The computer was strapped to this trolley and wheeled from classroom to classroom. Its arrival in a lesson was announced by the clatter of metal wheels on linoleum floors, followed by the sharp, piercing, dual-tone beep as the machine was powered on. For a brief window in the mid-1980s, Acorn held an astonishing monopoly on British digital education. Available records suggest that at its peak, the BBC Micro commanded 80% of the UK school computer market. It was an adoption rate that no single technology company has managed in British education since. In a British school where one computer might serve a room full of pupils, the right machine did not merely run software. It decided who first saw code move on a screen, who discovered games as systems, who imagined work beyond the high street, and who felt that the future had finally entered the classroom. To manage this immense scale, Acorn deployed Econet, a low-cost local area network system that allowed multiple BBC Micros in a single room to communicate with each other, sharing a single expensive floppy disk drive or a printer. Instead of a standalone machine on a trolley, secondary schools began building dedicated ICT rooms. Pupils sat at rows of BBC Micros, their screens glowing with the prompt of BBC Basic. A teacher could send files across the network, turning an isolated lesson into a connected system. Britain was building early local networks in schools years before most homes had ever heard of the internet. But a computer without software is just an expensive heater. What cemented the BBC Micro in the cultural memory of an entire generation was what loaded onto the screen. For most primary school pupils, software did not arrive on disks. It arrived on cassette tapes. A teacher would type the specific command to read the tape, and the classroom would fill with the harsh, screeching static of audio data being converted into digital instructions. It was a slow, fragile process. A slight knock to the desk or a dirty tape head could crash the loading sequence, forcing the class to wait another 10 minutes. When the loading did succeed, it often revealed Granny's Garden. Developed by Mike Matson, a British teacher, and published in 1983, Granny's Garden was an educational adventure game. It was visually primitive, relying on the BBC Micro's teletext-style graphics mode, which used blocks of solid color to draw blocky trees and a menacing witch. But the technology was not the point. The game required pupils to use logic, memory, and problem-solving to navigate a magical kingdom. It forced a group of children crowded around a single monitor to debate their next move, turning computing into a collaborative social exercise. Granny's Garden proved that a school computer did not need arcade-perfect graphics to hold a classroom in absolute silence. Beyond the school gates, the BBC Micro had spawned a sprawling secondary ecosystem. The high street began to reflect Acorn's dominance. W.H.S. Smith and John Menzies cleared shelf space for thick computer magazines dedicated exclusively to the machine: the Micro User, Acorn User, and B-Bug. These publications were not just news, they were delivery mechanisms. They contained pages of printed code, type-in listings that users would manually copy into their machines at home to create simple games or utility programs. This ritual turned passive consumers into bedroom coders. If a child made a typing error, the program would crash, forcing them to learn how the logic actually worked in order to fix it. The machine was teaching Britain how to build the digital world, but it was about to prove that it could also push the boundaries of what a microcomputer could mathematically achieve. While primary schools used the machine for blocky educational adventures, the sheer processing power of the BBC Micro attracted a different kind of developer. In late 1984, two Cambridge University students, David Braben and Ian Bell, released a piece of software that fundamentally changed British computing history. Elite was a space trading simulator featuring wireframe three-dimensional graphics. At the time, rendering fast, 3D movement on a home computer was considered mathematically impossible without expensive, dedicated hardware. The Model B had only 32 kilobytes of memory. To fit an entire universe of 8 galaxies and thousands of planets into that confined space, Braben and Bell used procedural generation, a mathematical technique where the computer creates the environment on the fly using algorithms, rather than storing every detail on a floppy disk. When Elite loaded on a BBC Micro, the machine did not just play a game, it simulated a universe. It proved to an entire generation of bedroom coders, young enthusiasts writing software in their homes, that British hardware could execute world-class engineering. By 1985, the BBC Micro had reached its absolute zenith. It was no longer just a government-backed experiment. It was a national institution. The machine had cultivated a fiercely loyal developer ecosystem, a network of software houses, accessory makers, and publishers built entirely around Acorn's hardware. Companies like Superior Software and Acorn Soft released titles that were technically brilliant and uniquely British. If a pupil wanted to play Revs, a highly realistic Formula 3 racing simulator that calculated aerodynamics and suspension geometry, they needed a BBC Micro. The machine's physical design encouraged constant expansion. At the bottom of the heavy beige casing sat a proprietary connection called the tube. This interface allowed users to plug in a second processor, an external unit that took over the heavy mathematical lifting while the BBC Micro handled the graphics and keyboard input. A school lab could buy a standard machine, and a university researcher could later upgrade it to rival the speed of a corporate workstation. The BBC Micro was not a closed box, it was a foundation. The physical presence of the platform was everywhere. Weekend computer fairs were packed with traders selling third-party ROM chips, read-only memory chips that plugged directly into the computer's motherboard to add new software instantly, without the agonizing weight of a cassette tape. The BBC Micro had become the undisputed center of gravity for Cambridge computing. Yet the very factors that made the machine an educational and technical triumph were beginning to isolate it from the rest of the world. Acorn had built a premium machine with uncompromising quality. The thick plastic moldings, the fast processor, the complex analog ports, and the exceptional mechanical keyboard meant manufacturing costs remained stubbornly high. The DTI subsidy, the government scheme that paid half the cost for schools, masked this economic reality. Inside the school ICT room, the BBC Micro was the default choice. But outside the classroom, the British public was buying differently. In high-street electronics shops like Dixon's, Boots, and W.H. Smith, parents were looking at the $399 price tag of a Model B and comparing it directly to the Sinclair ZX Spectrum, which sold for under $130. The BBC Micro was a heavy-duty public service Rolls-Royce in a consumer market that increasingly wanted an affordable runabout. The platform had won the trust of teachers, the loyalty of developers, and the imagination of a generation. But a crack was forming in the business model. Acorn was dominating an artificial market created by government funding, while the global industry was moving in an entirely different direction. The classroom belonged to Acorn, but the pupils eventually had to graduate, and the world outside the school gates was speaking a different language. The first crack in Acorn's dominance was not a dramatic hardware failure. It was a quiet financial realization inside a high-street electronics shop. By 1984, a family walking into a branch of Dixon's or W.H. Smith to buy a home computer faced a stark choice. On one shelf sat the Sinclair ZX Spectrum, priced aggressively under $130. Next to it was the Amstrad CPC 4634, a complete system including a built-in cassette deck and a color monitor for $299. And then there was the BBC Micro Model B. Without the government's DTI subsidy, which was strictly reserved for educational institutions, the machine still cost $390 just for the keyboard unit. Acorn had built an uncompromising heavy-duty machine, but they were trapped by their own engineering standards. The thick plastic molds, the fast processor, and the complex analog ports meant they could not dramatically lower the manufacturing cost. The BBC Micro was the most respected machine in Britain, yet it was steadily losing the home consumer market to cheaper mass-produced rivals. Acorn attempted to solve this by releasing the Acorn Electron, a stripped-down, budget-friendly version of the BBC Micro designed specifically to capture the Christmas market of 1983. But catastrophic manufacturing delays meant the machines did not arrive in shops on time. High-street shelves remained empty during the most important retail window of the year. Parents bought Sinclair and Commodore machines instead. The bedroom coding generation, the teenagers writing software at home, began to drift away from the Acorn ecosystem. The machine that dominated the classroom was becoming too expensive for the bedroom, but the true systemic threat to the BBC Micro was not the British high street. It was an American standard quietly crossing the Atlantic. Inside the secondary school staff rooms and local education authority offices, a profound shift in thinking was beginning to take hold. The BBC Micro had successfully taught a generation how to program in BASIC and how to understand raw computer logic. But as the mid-1980s progressed, computing was changing. It was transitioning from a specialized scientific subject into a standard administrative tool. The global business world had overwhelmingly chosen the IBM personal computer, a beige functional machine running an operating system called MS-DOS, controlled by a rising American company named Microsoft. When a British pupil left school and entered an office, they were not asked to write procedural code for a robotic turtle. They were asked to type a document in WordPerfect or build a financial model in a Lotus 123 spreadsheet. The BBC Micro was an 8-bit machine. Its processor could only handle a limited amount of memory and data at once. The IBM PC and its clones were 16-bit machines, capable of running complex professional software. A painful realization crept into British education. Teaching pupils on a unique British platform was no longer preparing them for the global workplace. The educational moat began to drain when schools decided they needed to teach standard office skills rather than pure programming. A new competitor began to displace Acorn in the school computer room. Research Machines, another British company entirely focused on education, released the RM Nimbus. The Nimbus was not a perfect IBM clone, but it was a 16-bit machine that looked and behaved much more like a professional office desktop. It ran a version of MS-DOS. It felt serious. When school IT buyers looked at their budgets, they began to turn away from the BBC Micro's red keys and towards the beige professionalism of RM and eventually standard IBM-compatible PCs. The ecosystem loop that had protected Acorn was breaking. A platform, the technology system that other products build around, relies on momentum. As schools stopped buying new BBC Micros, educational software developers noticed. Publishers began writing their new programs for MS-DOS instead of BBC Basic. Without new software, even the schools that remained fiercely loyal to Acorn found it harder to justify buying another machine. Acorn was fully aware of this existential threat. They knew the 8-bit era was ending, and they knew they could not survive simply by selling older machines to aging school networks. In 1987, they launched a stunning counterattack, the Acorn Archimedes. The Archimedes was a technological marvel. It abandoned the old BBC Micro architecture entirely and used a brand new, blisteringly fast processor designed completely in-house at Cambridge, the Acorn RISC machine, or ARM. It featured a graphical user interface, a mouse, and processing power that made contemporary IBM PCs look primitive. It was in many ways the ultimate British computer, designed to reclaim the schools and conquer the professional market. But technology history is rarely decided by the best hardware. It is decided by the largest ecosystem. The Archimedes was a brilliant British invention, but it was stepping into a world that had already agreed to speak an American standard. When Acorn launched the Archimedes in 1987, it was an engineering triumph. It ran a graphical user interface, a visual way of interacting with a computer using windows, icons, and a mouse rather than typing raw text commands. It was powered by the ARM processor, which made it blindingly fast compared to the sluggish PCs of the era. But the Archimedes was a commercial island. It was a brilliant British machine trying to hold back an American ocean. By the early 1990s, the global technology market had made its decision. The future belonged to the IBM-compatible PC. Microsoft released Windows 3.0, providing a graphical interface that, while technically inferior to Acorn's RISC OS in many respects, ran on cheap, mass-produced hardware. The most devastating blow for Acorn did not happen in a corporate boardroom. It happened in British staff rooms and local education authority offices. The generous government subsidies that had placed the BBC Micro in 80% of schools had long since dried up. When schools needed to upgrade their aging 8-bit machines, they faced a stark choice: buy the expensive proprietary Acorn Archimedes or buy standard PC clones. Parents and school governors began to exert pressure. They argued that teaching a pupil how to use Acorn's RISC OS was doing them a disservice. The real world outside the school gates, the offices, the banks, the universities, ran on MS-DOS and Windows. To prepare children for employment, schools felt compelled to teach the global standard. The school computer room, once a sanctuary of British engineering and eccentric coding, was slowly transformed into a sterile environment of beige PC towers running Microsoft Word and Excel. The heavy metal trolleys carrying BBC Micros were quietly wheeled out of classrooms and pushed into storage cupboards, replaced by rows of fixed desktop PCs. This loss of the educational monopoly shattered Acorn's ecosystem. Network effects, the pattern where a product becomes more valuable as more people use it, began to work in reverse. Because schools were buying PCs, educational software publishers stopped writing new programs for Acorn machines. They shifted their development teams to Windows, where the global user base numbered in the millions. Without new software, the remaining Acorn loyalists had fewer reasons to stay. The high street reflected this brutal new reality. If a customer walked down the aisles of a newly opened PC World, the massive retail warehouses that were replacing small independent computer shops, they would find endless shelves of boxed PC software, rows of multimedia PCs, and perhaps, hidden in a dusty corner, a single shelf of discounted Acorn titles. The physical space dedicated to the British platform was shrinking to nothing. Computer magazines dedicated to the BBC Micro and the Archimedes began to merge, shrink, and eventually fold. The tight-knit community of bedroom coders either moved on to programming for standard PCs, shifted to writing games for Japanese consoles like the Sega Mega Drive, or stopped coding entirely. The culture of typing in raw, basic commands from a magazine page had been replaced by the convenience of buying a CD-ROM. Acorn's corporate structure buckled under this relentless pressure. As early as 1985, the company's financial difficulties had forced them to sell a controlling stake to the Italian technology giant Olivetti. Throughout the 1990s, Acorn tried to pivot, desperately searching for a market that did not require competing directly with Microsoft and Intel. They attempted to build interactive television, set-top boxes, and stripped-down network computers. None of it achieved the scale required to sustain a major hardware manufacturer. By 1998, the battle was over. The company that had once taught an entire nation how to code could no longer justify its own existence as a computer maker. The Acorn Group was broken up and restructured. The computer division was eventually shut down, meaning the final end of support, the point when a company stops providing updates, fixes, or official assistance for a product, arrived for the last Acorn machines. The collapse was total. The educational budget shifted. The software houses moved on. The magazine shelves cleared. The high street shops looked away. The red keys were unplugged. The school trolleys were emptied. The company fractured. The brand disappeared. The classroom belonged to Microsoft. Acorn, the computer company, could not survive the global standard. But inside their abandoned machines, a different kind of architecture was already preparing to conquer the world. When Acorn Computers dissolved as a workstation manufacturer in the late 1990s, it marked the end of Britain's boldest attempt to build an independent hardware titan. The company's brand name was quietly stripped from the high street. Its desktop operating system retreated into niche enthusiast corners, and the heavy plastic cases that once dominated British education were systematically replaced by uniform gray PC towers. Yet the collapse of Acorn's hardware business concealed one of the most extraordinary paradoxes in industrial history. Back in 1983, when Acorn's engineers needed a faster, more efficient processor to succeed the 8-bit BBC Micro, they surveyed the existing microchip market and found nothing that met their needs. Led by Sophie Wilson and Steve Ferber, a small team in Cambridge designed their own 32-bit reduced instruction set computer processor, the Acorn RISC machine, or ARM. When Acorn, as a PC manufacturer, began to falter in the early 1990s, that chip design department was spun off into an independent company called ARM Limited, backed by Apple and VLSI technology. Acorn, the computer maker, vanished from the high street, but ARM, the chip architecture, survived to conquer global technology. Because the ARM processor had been designed to run efficiently inside a compact computer without requiring heavy cooling fans or massive power draws, it turned out to be the perfect silicon foundation for a mobile world. As battery-powered electronics evolved from crude handheld organizers into modern smartphones, global technology companies turned to Cambridge for their processor designs. Today, the direct descendant of an architecture built to power an 8-bit British classroom computer, resides inside virtually every smartphone, tablet, and smart device on Earth. Billions of microprocessors across the globe carry a design heritage born in a Cambridge office during the quest to upgrade the BBC Micro. Within the United Kingdom, the BBC Micro survives not merely as an industrial footnote, but as a deeply preserved physical culture. At the Center for Computing History in Cambridge and the National Museum of Computing at Bletchley Park, working Model B computers sit on display tables, their cooling vents clean, their red function keys still responsive to touch. Enthusiasts gather at retro computing fairs to trade original cassette tapes, 5.25-inch floppy drives, and expansion ROM chips. Developers maintain active emulation projects like BBEM and hardware recreations on FPGA boards, carefully preserving thousands of educational software titles, game files, and magazine type-in code for future generations. The BBC archive itself has digitized the original computer literacy project broadcasts, preserving the exact television lessons that first introduced microcomputing to the nation. This preservation culture exists because the BBC Micro passed a crucial test. It was never just a consumer gadget. It was a national pedagogical promise. In an era before closed app stores, locked file systems, and endless algorithmic feeds, the BBC Micro demanded that its users understand how hardware and software interacted. It did not present computing as a magic black box designed for passive consumption. When a pupil turned on a Model B, the machine greeted them with a simple prompt and a blinking cursor, inviting them to control the hardware through BBC Basic. It taught an entire generation of British children that technology was a system you could write, inspect, and master. That philosophy directly inspired the next revolution in British computing education. In the late 2000s, a group of academics and engineers in Cambridge, including Eben Upton, who had grown up using the BBC Micro in school, noticed that incoming university computer science students no longer possessed foundational programming skills. They had grown up using polished, closed consumer software rather than open, programmable hardware. To solve this, they created the Raspberry Pi, a low-cost, credit card-sized computer designed explicitly to revive the spirit of the BBC Micro in British classrooms. The Raspberry Pi Foundation built an affordable board with exposed pin headers, allowing pupils to once again connect sensors, motors, and physical experiments directly to a computer. The spiritual successor to the BBC Micro emerged from the exact same Cambridge lineage, created by people who remembered what it felt like to program a machine on a metal school trolley. The story of the BBC Micro is ultimate proof of a peculiar British trajectory. The United Kingdom launched a public service computing initiative that conquered 80% of its schools, cultivated a generation of bedroom coders, and birthed a software ecosystem of extraordinary technical ambition. It then watched as that domestic market was absorbed by global standards, American operating systems, and mass-produced foreign PCs. Britain failed to maintain a dominant PC hardware empire, but in failing, it created the foundational chip architecture that powers the modern mobile era. The computer maker died, the classroom changed, but the underlying silicon conquered the world. If you grew up with the red function keys, loaded games from cassette tape, or typed code from a magazine page, subscribe to Forgotten British Tech Empires. Every week, we tell the story of the machines, platforms, and high street names that taught the country what the digital future felt like, and what happened when the market moved on. See you in the next video. Somewhere in a quiet storage cupboard of a comprehensive school in Cambridgeshire, an original BBC Micro Model B sits inside a softened cardboard box, its distinctive red function keys dulled by decades of dust, resting beside a coiled gray power lid and a metal trolley that once carried the digital future from classroom to classroom.